All right, Physics 2, welcome back to part 2 of Thursday's lecture. So we're going to be continuing on with our discussion of magnetic force in chapter 20 of Matter and Interactions. Now we're going to be looking at magnetic force in a moving reference frame. So remember, moving particles experience magnetic forces, moving charged particles experience magnetic forces in a way that stationary charged particles do not. And remember, the beauty of physics is that motion is within the eye of the beholder, meaning motion is within the observer. So motion is determined by the reference frame or observer. Okay, so I want you to think back to our thought experiment about the charge tape experiment where we had the charge tape. So we had somebody who was stationary, who had some charge tape that was just sitting there, and then we had somebody that was running around, observing the charge tape as well as magnetic field. So maybe, I believe she was also holding charge tape. So one of them is going to see only a force related to electric fields, and the other of them is going to see a force related to both magnetic field and electric field. So if she is observing this charge tape from a moving reference frame, that charge tape is going to appear to be moving. And so she's going to see a combination of electric and magnetic fields as a result, whereas this person is only going to observe the force for this object from electric forces. Okay, so let's do a little bit more detailed analysis. All right, so let's consider two moving protons. So this is a much better example than that one. Ooh. Okay, so we've got our two moving protons, plus. So they both have velocity in the same direction. So they're just moving in positive x. So we've got the r hat vector between them, and we've got some distance r from which they are separated. And we're going to look at some forces. So from the perspective of particle 2, we're going to have the field from 1, so this is 1, 2, and we're going to have the force. So F21 from the proton is equal to Q2E1. So F21 is equal to 1 over 4 pi epsilon naught E2 r squared times 0 minus 1, 0. So in this case, since it's going down, we can just put minus 1 in for our unit vector. All right, so this is the situation that we're going to be analyzing. So, and just by the way, the force actually is a little bit different as these particles are moving, but we're going to just use a standard assumption. Okay, so we have an expression for our electric force right here. And now we want to look at our magnetic force. We've got electric force, and now we want to look at magnetic force, or F sub B. And so for this, there's something that we need that we don't have. We're going to need the magnetic field from particle 1 at location 2. So location 1 location 2. Okay. So, but we know how to calculate magnetic fields due to particles. So B1 is equal to mu naught over 4 pi Q1 V1 cross R hat divided by R squared. So B1 is equal to mu naught over 4 pi EV over R squared sine of 90 degrees. So in this case, the two are perpendicular to each other. So we can see that here, using that cross product V cross R. So we can see that B is into the page using the right-hand rule. So again, V, line your right hand up with V, cross it towards our hat. Our thumb is pointing down, not up, down, into the page. So, is into the page using the right-hand rule. So, all right, so next up we want to look at F21 magnetic, which is equal to Q2 V2 cross B. And so F21B is equal to mu naught over 4 pi E2 V2 over R squared, and it's going upward. Okay, so let's go ahead and draw another diagram and sort of update everything. So we've got our two little protons that are traveling with V. We've got our unit vector between them. And so we've got our magnetic field at 1B. We can see the sign there, it's going into the page. And we've got our electric field from 1, and we have our F21E plus. So, and we've got F21B is equal to Q2 V2 cross B1, and F21E is equal to Q2 E1. So here is our updated setup for the electric and magnetic fields and the forces between them as a result of the two particles moving. All right, so let's make this a little bit more interesting. I know it's already mind-blowing, but we're going to blow your mind some more. And let's look at the ratio of the magnetic and electric forces on proton 2. All right, so because something very interesting is going to come out. So ratio of magnetic and electric forces on proton 2. All right, so F21B over F21E is equal to mu naught over 4 pi E2 V2 over R squared divided by 1 over 4 pi epsilon naught. That's a pi, not a mu. E2 over R squared. So we can see this is equal to, got some cancellations, bam, 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 bam. So this is equal to V squared over 1 over 4 pi epsilon naught divided by mu naught over 4 pi is equal to V squared over 9 times 10 to the 9 divided by 1 times 10 to the minus 7, plugging in the values for 1 over 4 pi epsilon naught and mu naught over 4 pi. This is equal to v squared over 3 times 10 to the 8, quantity squared, is equal to v squared over c squared. Wow! I told you mu naught and epsilon naught was going to be important later. So it turns out the speed of light is very important to understanding magnetic and electric forces. And we're building to something really beautiful here that's going to unfold as we continue to move through this class. By the way, on your own, prove the units work out. I'm going to give you a big hint. They will. All right, so what we can see from this is that when your velocity is much, much smaller than the speed of light, you get a magnetic interaction that is weaker than electric interactions. And then if V approaches C, then the magnetic force can be comparable. To the electric force. All right, so pretty cool. Okay, so we've got two fields, two forces. So of course what this is leading to is another application of the Lorentz force. So let's calculate the Lorentz force on proton 1 due to proton 2. So remember, we always want to know who is observing this problem, from which perspective are we looking at? So now we're looking at perspective 1. Okay, so the Lorentz force F is equal to Q times E plus Q V cross B. So we already know the electric force is downward. And the magnetic force is upward. So F net equals 1 over 4 pi epsilon naught. Actually, there's E squared over R squared minus mu naught over 4 pi E squared V squared over R squared, and this is equal to 1 over 4 pi epsilon naught E squared over R squared 1 minus V squared over C squared downward. So basically what you're looking at here is these two particles, as they are traveling, they're going to start to see, oops, here we go, let's put that on screen, a curved path as they're going to start to move away from each other. Okay, so this is what happens if we are a stationary observer. Now let's bring a little bit of relativity into this. So we've got two people who are going to be observing these particles. So I always like to bring my family into it. So here we've got my husband Piper. He is sitting still and he's watching the protons move because he can do that in pretend La La Land. Here is my daughter Esther. There she is. And she is running with the protons. Because if anybody can run with protons, it's got to be her. So What Piper is going to see is he's going to see this curving motion as they go up towards the ceiling. So he's going to view the curving paths, and the force is somewhat weakened from the magnetic force. Whereas Esther, because she's running with them, is just going to see just straight lines. So she sees the protons repel in straight lines. So from her perspective, because she's running along with them, they might as well be at rest. So in both cases, for both cases, the protons end up on this, protons go to the ceiling and floor, assuming they're in a room. Oh my goodness, I can't even spell floor today. Wow. All right, and now let's just make this more interesting. Let's say both of them had a timer, and they would both see them go to the ceiling and the floor, but because Piper is sitting still, he will measure a longer time than Esther. So Piper will measure a longer time than Esther. So the process takes the same amount of time, but Esther's timer is in a moving reference frame, and therefore time moves more slowly because V is not equal to 0. And this, by the way, is the crux of the famous twin paradox, where if you send one twin into space and he's constantly moving, he will experience time more slowly than the twin who's left on Earth. So, of course, if you like discussions like this, you should keep going in physics, because we get to do a lot more of this in Physics 3 or modern physics, and you certainly get to do more of this in electromagnetism. Should you have the opportunity to take this class. All right. Let's move on and talk about magnetic torque. So, magnetic fields can cause a current-carrying wire to twist. Magnetic fields are very cool little things. I mean, we've known magnetic fields were cool for a long time. Let's face it, we all played with magnets, and we all know how much fun they are. Okay, so let's take a closer look at this phenomenon. So let's say that we had a wire. I'm going to make it a rectangular wire. Oh, that's a really bad rectangle. And we're running a current through it. And we've got this wire in a magnetic field. So we're going to say the magnetic field is coming right at you. You can see the points of those arrows pointing up. And so we've got our horizontal axis right here. And we have the width of this and the height. Okay, so current's running around, we've got a magnetic field, and let's start breaking the situation down. All right, so in this particular case, the current loop is free to rotate. So nothing is holding it in place. So if that magnetic field wants to rotate it, it's willing to go along with it. All right, so on side H, so I'm going to actually leave this picture where I can, so we're going to look at side H right here. We can see that the magnetic force is horizontal and points outward. And this will result in stretching the loop. on sides W, magnetic force is horizontal and makes the loop want to twist. No word if it wants to shout too. So here, the W side, we can see the relationship between the current and the magnetic field giving us magnetic force. So let's look at a side view. So we've got the experience of the magnetic field So in this case, the magnetic force will twist the loop counterclockwise. So we can look at this. We've got, so let's start drawing some vectors onto this. So we've got the magnetic field that was in there already. We have the force, which is equal to I WB, and the force, which is equal to I WB. And in the middle, we have something that we've seen before. Mu is equal to current times area, which is equal to current times height times width. So if you recall, mu is the magnetic dipole moment. And let me go ahead and move that up. So mu is the magnetic dipole moment. So in our rectangular loop, area is equal to width times height. Mu is equal to current times area. Therefore, mu is equal to current times height times width. And the coil is going to twist in the direction to try and line up with the applied B. So mu wants to hang out in the same direction as B. If it can't get there, it's going to try and twist to get there. So what we are dealing with, of course, is torque caused by a magnetic field around the area of a current carrying wire. So let's think about some torque. So what we want to do is we want to express torque in terms of the magnetic field B. All right, so let's update our pictorial representation in just more detail. Okay, so we've talked about mu pointing up at the middle of the wire. We've got our magnetic field B. I need to do more colors. Okay, so we've got some angle theta. So we have h over 2 here and h over 2 on this side. Okay, so we've got our force, which is equal to I WB, and then the perpendicular component of the force, F perpendicular, is equal to I WB sine theta. And we have force in the horizontal, which is equal to I WB, and the perpendicular component, IWB sine theta. We have theta here and theta here. All right, so this is the updated picture, of course. For those of you following along in matter interactions, there is a much more detailed and straighter line drawing in your book. But since mu is equal to I times W times H, and torque is equal to mu cross B, so then we would see that mu, the magnitude of mu and B sine theta is equal to mu B sine theta. And from this we can get our expression for torque on a magnetic dipole. So torque is equal to mu cross B, and the magnitude of torque is equal to mu B sine theta. And this works for any shape. Put this where you can see it. And on your own, I want you to think about why this relationship is true. You can go back and use this drawing or do it with equations. All right, so this concludes part 2 of Thursday's lecture. I will see you next time for Monday's lecture.